Welcome to this explainer. We're actively guiding you through mastering PVsyst so you can design your very first grid-connected solar project. Now, if you've ever stared at a totally blank screen in a solar design program wondering where on earth to begin, or if you just want to make sure your yield predictions match the real world, you are in exactly the right place. Today, we're taking a highly structured step-by-step approach to building a reliable, highly bankable solar simulation. You know, the kind that investors will actually trust.
Here is our roadmap for today. We're going to start with a quick welcome to the workspace, then compare projects versus system variants, and cover setting the geographical site. After that, we'll dive into defining solar panel orientations, designing the subarray system, and wrap it all up by calculating detailed thermal losses. Let's get right into it.
All right, Section 1. Welcome to the PVsyst workspace. Because, well, before you can build a house, you kind of need to know the layout of your tool shed, right?
So, what actually is PVsyst? At its core, it's a comprehensive software tool for the simulation, optimization, and analysis of photovoltaic systems. But it's really not just about drawing solar panels on a roof. It's a rigorous analytical beast that factors in shading, grid availability, panel degradation, and real-world weather to give you incredibly detailed financial and energy assessments. Basically, it's the industry's gold standard for proving to stakeholders that your system will do exactly what you claim it will.
When you first fire up the software, the main page cleanly divides your workflow into 3 buckets: project design, utilities, and your user workspace. It's specifically built this way to stop you from getting overwhelmed. You have your core design environment on the top left, your databases on the right, and a dedicated workspace folder at the bottom where your custom components and files live safely. It acts as a highly structured gateway, keeping all those complex simulations perfectly organized.
Now, the software absolutely handles standalone setups, which force you to configure battery storage and even specialized pumping systems for agricultural use. But our primary focus today, we're locking in on grid-connected systems. That is, by far the most common use case in the industry. Whether you're mapping out a 5-kilowatt residential rooftop or a massive 100-megawatt utility farm, mastering that grid-connected flow is the absolute foundational skill you need as a solar designer.
Moving right along to Section 2, Projects versus System Variants. Let's unpack how PVsyst organizes its data, because this is exactly where a lot of beginners trip up. Think of it like this. The project is your absolute, unchangeable foundation. You're locking in the physical reality, the exact coordinates, the weather it experiences, and the ground reflectiveness, or FAR albedo. The variant, on the other hand, is the house you build on top of that foundation. It's where your engineering creativity gets to shine. You can test out variant A with string inverters, swap to variant B with central inverters, or test variant C with totally different panel angles, all while resting securely on that single, solid project foundation.
On the project dashboard, the interface literally forces you to work logically from top to bottom. The top half is dedicated entirely to your site and weather data. Then, the bottom half houses the specific tabs for your variant, things like orientation, layout, and detailed losses. It's a great failsafe, ensuring you never start designing a system without first locking in the environmental realities of the site.
Okay, Section 3, Setting the Geographical Site. This is where we breathe life into the simulation by pinning it to an actual spot on the map.
You've got 3 sequential steps here. First up, define your project name and punch in the exact coordinates. Second, the software uses those coordinates to pull in the monthly weather data. And step 3 is absolutely crucial. You have to generate hourly synthetic values, often called a TMY. Since the sun moves and clouds roll by constantly, PVsyst needs that hour-by-hour breakdown to run its precise mathematical models for your site every single day of the year. Here's the catch, though. You have to choose your weather provider wisely. Understanding the difference between meteonorm and TMY data is going to drastically impact your P50 and P90 yield estimates. Meteonorm uses stochastic models to create a synthetic yet highly accurate hourly profile from monthly averages. TMY data actually stitches together historical measurements from at least a decade to create a typical year. Your choice here directly impacts how banks view the financial risk of your project. Accurate data means bankable data.
All right, on to Section 4, Defining Solar Panel Orientations. We have our site locked in. Now how are we actually catching those rays?
It all comes down to some basic geometry. Plane tilt is just how far off the flat ground your panels are angled. Azimuth is the direction they face relative to the equator, so due south in the northern hemisphere is 0.
And honestly, PVsyst takes the guesswork right out of this. It has a built-in optimization tool that maps out exactly how tweaking your tilt and azimuth will impact your annual yield based on your latitude. It seriously saves you hours of trial and error. Now, if you're upgrading from fixed sheds to trackers, you have to set mechanical constraints, like your phi limits, which are basically the maximum rotation angles of your gear. But more importantly, you need to decide if you're using a backtracking strategy. It's a fascinating engineering trick. Early in the morning or late in the evening, trackers will actually rotate slightly away from the sun to stop one row from casting a shadow onto the row behind it. It briefly sacrifices perfect sun alignment, but it maintains the total power output of the system and drastically cuts down on electrical mismatch losses.
Moving to Section 5, designing the subarray system. We've got the sun and the angles. Let's talk about the actual hardware.
Here is a golden rule that PVsyst strictly enforces to maintain a healthy operating condition. Every single string connected to a single MPPT input has to use identical modules, and the exact same number of modules in series. Why? Because mixing different modules or string lengths on a single MPPT in the real world severely bottlenecks your power generation. It completely confuses the inverter's tracking algorithms and leads to massive inefficiencies.
When sizing your inverters, aiming for a 1.25 ratio of PV array nominal power to inverter AC power is a fantastic rule of thumb. You might be wondering, why intentionally oversize the DC side? Well, because in the real world, panels almost never hit their perfect, lab-rated maximums thanks to heat, minor shading, and atmospheric dust. If you match your panels and inverters exactly 1-to-1, you're paying for expensive inverter capacity you're literally never going to use. A 1.25 ratio optimizes your budget while ensuring maximum energy capture.
Finally, Section 6, calculating detailed thermal losses. This is our last critical design step, and it's where we cross from basic geometry straight into real-world physics.
It's a simple, undeniable rule. As solar panels heat up, they lose output voltage. A panel baking in the hot sun can easily clear 60 or 70 degrees Celsius. If you size your array without thinking about this thermal reality, your string sizing is going to be completely wrong. That leads to dangerous inverter overloads or severe underperformance. We're talking about inverters literally shutting down right when the summer sun is at its absolute peak. That can cost your project thousands in lost generation.
To get a genuinely accurate simulation, you have to plug in specific heat loss factors, or use of values, based on your mounting setup. And the differences here are wild. A freestanding array out in a field gets great airflow, letting the heat escape, giving it a factor of 29. But an integrated rooftop system, where the panels are sitting right flush against hot shingles, the heat is trapped, lowering its cooling ability to a factor of just 15. The hotter the panel, the lower the efficiency. If you skip this variable, your yield report is basically useless.
Listen, whatever you do, do not just rely on standard manufacturer NOCIT ratings for this step. Those tests are run under highly specific, controlled laboratory conditions that your project is frankly never going to experience. By manually inputting the correct heat loss factor for your specific mounting type, you are forcing the simulation to embrace the messy, thermal reality of the outdoors. That is exactly what separates an amateur design from a true, expert-level, bankable simulation. And there you have it. You now have the foundation and the tools to build incredibly accurate variants. You know how to lock in the location, interpret the weather data, optimize your panel angles, string up a healthy subarray, and conquer those complex thermal losses. So it's time to grab your meteorological data, pick your panels, and fire up the workspace. What kind of grid-connected project are you going to simulate first?